Ladies and gentlemen, a very good morning. Welcome to seminar. First, let me introduce myself. My name is Chayakorn Srikong, student of Department of Aquaculture, Faculty of Fisheries, เกษตรศาสตร์ University กำแพงแสง Campus. Today's presentation is about effects of oceans acidification on juveniles, red skin crab, Paralithodes, camtschaticus, and tender crab, Chionoecetes, bairdi, growth, conditions, calcifications, and survival. Outlines. Number 1. Introduction. Number 2. Objective. Number 3. Material and methods. Number 4. Resource. Number 5. Discussion. Number 6. Conclusion. Without further ado, I would like to get started on the presentation about external anatomy of the red skin crab. Red skin crab. External ventral anatomy of the tender crab. Tender crab. Difference between tender crab vs red skin crab. Tender crab 4 pair of legs, 2 big crab, and red skin crab 3 pair of legs, 2 big crab. The red skin crab is biless and has spine more than tender crab. Number 1. Introductions. The higher the carbon dioxide content, the lower the pH value of the water, and the higher the ocean's acidity. Next, the pH of oceans globally has decreased by about 0.1 unit. Next, the chemical change in water affects many organisms living in the ocean. Next, calcifying organisms are thus to be particularly vulnerable as a lower pH increases the dissolution rate of calcium carbonates. Next, additionally, the embryo and larva of some species exhibit lower survival rates and lower growth rates. Next, in this study, we examine the effect of ocean acidification on the growth conditions, classifications, and survival of juveniles of two commercially important species of crab. Number 2. Objective. Next, effect of ocean acidification on crab growth, conditions, classifications, and survival. Next, in addition, we conduct this study over a long time period in order of differentiate between the short and long-term effects of exposure to acidified water. Number 3. Materials and methods. The experimental setup used for this water as ambient temperature and salinity, as we did not control the temperature, pH, and carbon dioxide. Next, control. Number 1. pH 6.0. Number 2. pH 7.8. Number 3. pH 7.5. Next, lava were released to the first cap state before being transported to the chloride slab insulated shipping container. Throughout the experiments, the crabs were fast to exist on a gel diet of jelly belly pus enhanced with cycloph ear powder and porous bones powder. The experiment was performed in 3 tanks at the same size as 120 liters. Next, 90 crabs per species were randomly assigned to each of the 3 treatments, 30 crabs per species per treatment. Next, if crab was placed in an individual holding cell made of plastic or PVC plate, diameter 5.1 cm with mesh screws on the bottom. Next, jellies, 5 randomly selected cells per treatment per species were monitored for pH and temperature. Next, weekly water samples were taken from the head tanks and sent to an analytical laboratory. Next, the pH, temperature, the acid dissolved in organic carbons, and alkalinities were analyzed with a one-way analysis ANOVA of variance. Next, crabs were checked daily for moulting or death. Next, dead crabs and exuvias were removed from the tanks for morphometric analysis. Picture A, red skin crabs. Picture B, tender crabs. Next, the tender crab experiment was started on June 4, 2010, and the red skin crab experiment on June 10, 2010. Next, the experiment ends on December 20, 2010. Total experimental duration was 199 days for tender crab and 192 days for resting calf. Next, degrades are typically used when modeling calf growth to exclude for the effects of temperatures in experimental treatment. During these experiments, mean daily temperature in individuals holding cells for resting calf and tender calf out. These experiments from June to December 2010. The average daily standard deviation not shown was 0.1 degrees Celsius. Next, table 1 points the mean and standard error HE of water chemistry parameter measures the RC and alkalinities and calculated or others. See text for details. In the three treatment during the experiment, percentage of cleft allies survival of cleft in controls and acidified water. Next, from picture A and picture B, the pH of the water decreased, causing the survival rate to decrease as well. And the survival rate of resting calf at pH level 7.5 was found to be equal to 0 points, unlike tender calf, which has a higher survival rate. Number 4. Results. Table 2 points models of survival for resting calf and tender calf linked using AICC. The aggregate information criterions corrected for small sample size. AICC model indicates how the molality rate was modulated as a function of treatment. See text for details. Case indicates the number of parameters. For resting calf and tender calf, it can be seen that they have the same length. This indicates that AICC survival rates were not significantly different. Figure 4 change in calf morphology in control and acidified water. Mean PC1 score standard error from principal components analysis of resting calf A and tender calf B. Morphometric for H most for calf health in control pH 7.8 and pH 7.5 water. Symbol with different letters beside them differ significantly within the small state. Note that calf size is inversely proportional to PC1 for both species. We conclude that a CP1 treatment is different and before experimenting intent with a pH of 7.8 cleft then to have larger than just control tanks. This can be seen from the average CP1. Next, PC2 was significantly different between treatment and has a positive relationship with pH 7.8 and pH 7.5 with the sharing distance has a direct effect on increasing the size of cleft. Table 3. Principal components analysis of resting calf morphometrics. PC1 and PC2 eigenvectors are significantly different morphologies, and when accounted for with ANOVA, the results are inversely similar. Figure 5. Growth of resting calf in control and pH 7.8 water. A. The carpet length in the tank control growth better at pH 7.8 and B. The waste mass of control waste more at pH 7.8. The score represents the individual's optimal model measurements and lie. Table 4. Principles components analysis of tender calf morphometrics. When eigenvector and ANOVA were reached, they show significant morphological difference. Table 5. Model of resting calf growth length using AICC. Model indicates how the two parameters A and B were modulated in all models and was allowed to vary slightly with calf number. Next step within treatment T indicates that the parameter was allowed to vary with pH treatment. See text for model detail. The AICC's value for us very slightly, but this results in very significant difference showing the different growth patterns of us. Figure 6. Growth of tender calf in control and acidified water. A. Shell weights with control tank and pH 7.8 tanks having similar percentage during the first and second modes. B. Waste mass control tanks and pH 7.8 having similar percentage during the first mode, the first time and the second time. The line represents the mean CWs always made after Earth moves. The distance between vertical jumps indicates the average duration of the modes. The final line high represents the mean CWs always made at the end of the experiment. This number represents the percentage of craft modes. The date time is achievement. Number 5. Discretion. Ocean acidification substantially reduce the growth, conditions, and survival of two phylogenetically diverse crab species in this long-term experiments. Resting crabs were particularly vulnerable, with all crabs drying within 95 days at pH 7.5. Next, classifications suggest that short-term exposure to moderate decrease in pH will have on long-term effects on the crab species. Next, the morphometry of both crab species was not evidenced by pH events after several months. Next, however, leverage developments as the lava state makes them more vulnerable to stress. The skin cap embryo and lava do exhibit slight differences in morphology when exposed to low pH, but the major difference is the depth. Embryo and lava health at low pH are slightly larger than those held in controlled water. Next, both species grow more slowly in low pH water. Again, red skin calves were more sensitive, showing a significant difference between the pH 7.8 and control treatment. Whereas for tender crab, the effect was not significant until the pH was reduced to 7.5. Next, in this long-term experiments, tender crab decreased calcifications in low pH water samples observed in a few other crustacean species. Figure 7 conditions index and calcifications in crab health in control and acidified water. Red skin crabs condition index A and standard crab B and percentage of calcium damage in red skin crab C and standard crab D as the S of the experiments bar are mean plus standard error difference bar. The latter as the top are very different. If the latter are the same, there is no significant difference. Number 6. Concretion. However, as pH level drops in surface water, the deep sea crab may begin to compete successfully for shallower water habitats. Finally, the research highlights the need for long-term exposure experiments to escalately predict the effects of ocean acidification. In our experiments increase in mortality and decrease in growth were not apparent during the first 3 or 4 months of exposure. Future research should focus on understanding the effect of ocean acidification as early historic stages for both species and on effects on inter-specific interactions under African conditions. Does everyone have any question? This brings me to the end of my presentation. Thank you for listening.